Please start with this chapter to learn about architectural optics. A good light environment is a necessary condition for people to work, study, and live normally, and has a direct impact on work efficiency and visual health. At the same time, lighting also affects the indoor heat and humidity environment and building energy consumption. Therefore, enough attention should be paid to lighting in architectural design, and lighting should be designed through quantitative calculation. Since the photoreceptor cells of the human eye are divided into pyramidal cells and rod cells, they play a major role in different light and dark environments, forming photopic and scotopic vision. Photopic vision refers to the vision that is mainly played by the pyramidal cells on the retina in a bright environment. It can recognize small details and colors and has strong adaptability to change in internal brightness. Scotopic vision refers to the vision that is mainly performed by rod cells on the retina in a dark environment. It has only light and dark perception, no color perception, cannot distinguish the details of objects, and has low adaptability to external changes. When the human eye sees radiation of the same part, it feels different brightness at different wavelengths. This phenomenon is called the peculiar effect, and the code representing this characteristic of the human eye is called the spatial luminous efficiency, with the ratio of the monochromatic radiant flux of lambda m to lambda that produce the same visual perception under specific photometric conditions. Radiant flux refers to the energy emitted by a radiation source per unit time, represented by phi-e. Lambda m is the maximum visual perception, which is 555 nanometer in photopic vision and 507 nanometer in scotopic vision. The spectral luminous efficiency of photopic vision is V lambda, and the spectral luminous efficiency of scotopic vision is V lambda prime. The basic photometric units are luminous flux, luminous intensity, illuminance, and brightness. Since the human eye has different sensitivities to electromagnetic waves of different wavelengths, the amount of light cannot be directly measured by the radiant power or radiant flux of the light source, so the luminous flux is used to measure it. Luminous flux refers to the radiant flux in the visible light range and perceived by the human eye. The unit is lumen, and the symbol is Lm. The luminous flux is equal to the sum of the products of the radiant flux of its wavelengths emitted by the light source and the spatial luminous efficiency of the corresponding wavelengths multiplied by the maximum spatial luminous efficiency. The maximum spatial luminous efficiency under photopic vision is 683. Next, let's do two exercises. First, find the luminous flux. It is known that the low-pressure sodium lamp emits monochromatic light with a wavelength of 589 nanometer, and its radiant flux is equal to 10.3 watt. This is the monochromatic light source that can only emit one wavelength. The no radiant flux is 10.3. From spectral luminous efficiency curve, it can be found that the spectral luminous efficiency corresponding to 589 nanometer under the vision is 0.769, and the luminous flux is equal to 5,410 lumen. Second, find the luminous flux. The monochromatic radiant flux of 500 watt mercury lamp is known. This is a light source that can emit 6 wavelengths. The data in the left two columns of the table are known conditions, and the spatial luminous efficiency found according to a given wavelength is listed in the third column. The product of the data in the second column and the third column and 638 is listed in the fourth column, and the total luminous flux is 15,613.2 lumen. The luminous intensity takes into account the different spatial distribution of the luminous flux emitted by different light sources, and is used to represent the spatial density distribution of the luminous flux. The differential sign can be removed when the luminous flux is uniformly distributed within solid angle. This picture shows a hollow sphere. The center is the light source and emits 5 luminous flux to the area A surrounded by A1, B1, C1, D1, and the angle formed by the area A to the center of the sphere is the solid angle omega. The angle alpha in this diagram is 0 degree, and omega is equal to A divided by the square of R. The unit of luminous intensity is candela, and the symbol is CD, which means that the light source emits a luminous flux of 1 lumen uniformly within a solid angle of 1 sterndon. Illuminance represents the luminous flux density on the illuminated surface. The differential sign can be removed when the luminous flux is uniformly distributed on the illuminated surface. When several light sources illuminate the illuminated surface at the same time, the illuminance is equal to the sum of the illuminance of each light source on the illuminated surface. The unit of illuminance is lux, and the symbol is Lx, which means that the luminance flux of 1 lumen is evenly distributed on the illuminated surface of 1 square meter. As can be seen from the figure A, the same light source has the same solid angle, and the illuminated area and the distance from the light source are different. This is the case when the light is perpendicular to the illuminated surface. That is, the incident angle is equal to 0. From the definitions of luminous flux, illuminance, and luminous intensity, it can be known that the luminous flux falling on A1, A2, and A3 is the same. The luminous intensity is the same, and only the illuminance changes with the illuminated area. From this, the relationship between luminous intensity and illuminance can be derived. That is, in 1 square law of distance. Figure B shows the case when the incident angle is not equal to 0. The A2 surface forms angle I with the A1 surface. The normal of A1 coincides with the ray, and the normal of A2 forms angle I with the ray. According to the definition of illuminance, phi is equal to A1 multiplied by E1 and equal to A2 multiplied by E2. Considering that A1 is equal to A2 multiplied by cosine I, it is diffuse that E2 is equal to E1 multiplied by cosine I. Considering that E1 is equal to I divided by the square of R, it is derived that E2 is equal to I times cosine I divided by the square of R. That is Lambert's cosine law. This formula is a relationship between luminous intensity and illuminance, and is suitable for point light source. When the size of the light source is less than 1/5 of the distance from the light source to the illuminated surface, the light source can be regarded as a point light source. Next, let's do an exercise. There is a 40-watt incandescent lamp hanging 2 meters above the table in the picture. Find the luminance of point 1 and point 2 on the table. It is known that the luminous intensity of incident angles from 0 degree to 45 degree is all 30 seconds. Since the luminous intensity is known, the relationship between the luminous intensity and the illuminance can be used to solve the problem. The angle I at point 1 is equal to 0 degree, and the angle I at point 2 is less than 45 degree, according to the Pythagorean theorem. Therefore, the luminous intensity of points 1 and 2 are both taken as 30 seconds. The R value of point 1 is equal to 2. The R value of point 2 can be obtained by finding the hypotenuse of 2 right-angled sides, according to the Pythagorean theorem. Comparing the calculation results, it can be seen that the illuminance of point 2 is smaller than that of point 1, which is caused by the larger distance. Think about it. How to increase the illumination? Add a lamp shading. What about tilting the work surface? 2 objects in the same position have the same illuminance, but can cause different visual perceptions in the human eye. The luminance is the luminous intensity per unit projected area. When the luminous intensities in the direction of the angle alpha are all equal, the differential sign can be removed. Since the brightness of the surface of the object is not necessarily the same in all directions, the angle alpha is marked under the brightness symbol L, indicating the brightness in the direction of the angle alpha with the normal of the light source. The common unit of brightness is nit. Brightness is sometimes used as a larger unit. The symbol is SB. Another unit of brightness is apostable. The relationship between illuminance and brightness refers to the relationship between the brightness of the light source and the illuminance it forms. In the figure, A1 is a light-emitting surface with the same brightness in all directions, and A2 is an illuminated surface. dA1 is a macro-element area on A1, which can be regarded as a point light source due to its small size compared with the distance from the illuminated surface. The luminous intensity of dA1 to point O is Di, and the luminance formed at point O is DE, which is equal to Di cosine I divided by the square of R. The relationship between dE and the luminous can be deduced, and then substituted into the solid angle to obtain the solid angle projection law. The illuminance formed by the entire light-emitting surface at point O is calculated by integrating. When the brightness of the light source is the same in all directions, the integration is omitted. Next, let's do an exercise. In a room, a 1 square meter window is opened on the side wall and the roof respectively. A table is placed in the middle of the room at the same height as the side window sill. The center of the table is 2 meters away from the side window, and the surface of the table is also 2 meters away from the roof. It is known that the brightness of the sky is equal to 1 step, and it is required to find the illuminance formed by each window on the desktop. Think of the window opening as a luminous surface whose brightness is equal to the brightness of the sky. As can be seen from the figure, the normal is drawn at the window opening and the center of the table, and the angle alpha and the angle I are marked. Since the brightness is known to find the illuminance, the relationship between the brightness and the luminance is used to solve it. Calculate the side window first, and use the Pythagorean theorem to calculate cosine alpha. Calculate omega and cosine I respectively, and substitute the results into the relationship between illuminance and brightness, and find that E is equal to 554 lux. Next is the skylight. Since the table is placed directly under the skylight, the angle alpha and the angle I are both 0 degrees. R is equal to 2, and E is equal to 2500 lux. It can be seen from the comparison of the calculation results that the same lighting area and the different positions lead to different lighting effects, and the lighting effect of the side window is not as good as that of the skylights. Think about it. How to calculate this problem if you consider the light blocking effect of the window glass? What kind of glass is good for light transmission?